Welcome back to Electric Fields. Today we are learning the math portion. So last time we looked at the electric field as a representation of the forces that an electric charge produces. But today we're actually going to define that mathematically as the force to charge ratio at every point in a space. So it's not quite the force, it's the force divided by the charge of the particle that's feeling the force. So that looks as you see below. The electric field at some point xy is equal to the force on a charge at xy divided by that charge. So if you remember back from Coulomb's law, we had force equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. If you take that force, which is the force on some particle Q, we'll say it's the force of particle 2 on particle 1, then that means the electric field on charge 1 due to charge 2 is this whole thing divided by charge 1. So the charge 1's cancel, and the electric field is merely 1 over 4 pi epsilon naught Q2 over R2. So the only thing the electric field is dependent on is the source charge, which is Q2 here, and how far away you are from that charge. So mathematically, that's what the electric field is and how we describe it quantitatively. Now, in real life, measuring electric field is only possible using a charge because electric charges are the only things that interact with electric fields. So, anytime we're measuring an electric field, we use a small positive test charge, find the force on it, and divide that by the charge of the test charge. So anytime you measure electric field in real life, gotta use a little charge to feel the force and figure out the value of the field at that point. So really, it's a pretty basic idea mathematically. We're gonna read this example problem and do it real quick and move on. It says an electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometers. What is the electric field due to the proton at the position of the electron? So we'll draw a quick picture. We've got a little proton here in the middle. I'm going to do a plus for proton. And then 0.053 times 10 to the negative ninth meters away, we have an electron. To find the electric field, we've just got to plug things in. So the force of Q1, which we'll say is the proton on Q2, we're going to find using Coulomb's law. Force equals 1 over 4 pi epsilon naught, which I'm just going to write as K because it's the same thing. K times Q1, which is charge of a proton, so 1.6 times 10 to the negative 19th coulombs, times charge 2, which the charge of electron is also 1.6 times 10 to the negative 19th coulombs, just negative. So I'm going to make that squared, divided by the radius between them squared. So 0.053 times 10 to the negative ninth squared. All right, so that is our force. To find the electric field due to the proton, you take that force and you divide it by the charge of the electron, which is 1.6 times 10 to the negative 19th coulombs. So if you want to simplify and cancel out there, you get that the the electric field equals K times 1.6 times 10 to the negative 19th, because one of them is going to cancel with the bottom, divided by 0.053 times 10 to the negative ninth squared. I really don't want to go get a calculator and do that, but I'll stop my video and do it for you right now. All right, back with the calculator update. If you type that in and you plug in the right value for K, you get that the electric field at that position equals 5.126 times 10 to the 11th, and the unit for electric field is newtons divided by coulombs, because it's the ratio of force to charge. You should also note, since this is a vector, that we need to have a direction with this, which is a little bit trickier with electric charge. So you might be tempted to say, well, it's pulling the negative towards it, so the field is towards it. But that's not how the electric field conventions work. And it's strictly a convention thing, but it is the convention for all physicists, so it's what we're going to do. So the convention for electric fields is that positive charges have fields pointing away from them and negatives have fields pointing towards them. So even though the negative charge is being attracted, we say the electric field itself is pointing away from the positive charge. So we would say, in our picture here, it would be to the right. So something to note is that when you're working with a negative charge in an electric field and you see all the electric field lines, it's going to be going the opposite direction of the arrows. All right, just like with forces due to multiple charges, when you have an electric field due to multiple charges, you superimpose, which simply means you add them to each other. So you find the field from one charge, you find the field from another charge, you add them together. It is going to require some vector addition. Our next example is a dipole. A dipole is a positive charge and a negative charge. So the dipole consists of positive and negative charge separated by 1.2 centimeters. What is the electric field strength along the line connecting the charges at a point 1.2 centimeters to the right of the positive charge? Okay. So the way we're going to do this is by calculating the electric field for each point charge and then adding them together. So at this point, we're going to stop using electric field equals force over Q, and we're going to use the more simplified definition for point charges, where you take the force KQ1, Q2 over R squared, and then divide it by one of the Q's. So you're just left with KQ of the charge you're finding the field of over R squared. Okay, so we just took that extra Q1 or Q2, whichever, and then divided it out because it's the charge or the force to charge ratio. So those cancel out and go away, which is great. So now we don't have to deal with all that. We just have KQ over R squared. And actually, I forgot to put it in the slide. Now I need to go do that for when I actually give this lecture in class tomorrow. But each of these charges has a magnitude of 1.5 nanocoulombs. So they are the same magnitude, both the positive and negative, just oppositely charged. So to calculate the field strength of the positive, we've got the electric field due to a point charge equals K. K is 9 times 10 to the 9th. Newtons times meter squared over coulombs squared. I need to be more consistent about putting my units in there because they're important. So it's that times Q, which is 1.5 times 10 to the negative 9th coulombs, nanos negative 9, divided by R squared. And R from the positive to the test charge there is 2.4 centimeters. Convert that to meters, you have 0.024 meters, and that's a quantity squared. So let me go calculator that out real quick. All right, and the numerical answer you get there is 2.34, and we'll round it off at 4 times 10 to the, let's see, 1, 2, 3, 4 times 10 to the 4th. And that is measured in newtons over coulombs. And you can see that now that I've actually put in the units. We've got meters squared, 1 coulomb gone, 1 coulomb gone, newtons over coulombs. So that is the electric field. I'm going to put a plus because it's for the positive charge. Now in the picture here, we would draw electric field lines away from the positive charge because that's convention. You draw them away from the positive. So the vector would be towards the right. So we're going to put 2.344 times 10 to the 4th newtons per coulomb to the right. Now we're going to do that same thing for the negative particle. The electric field of the negative equals 9 times 10 to the 9th newtons times meters squared over coulomb squared times the charge, which has the same magnitude, 1.5 times 10 to the negative 9th coulombs, divided by radius squared. The radius this time from the negative to the test is just 0.012 meters squared. And then we come up with an answer. And when you put that all in the calculator, you get that the electric field due to the negative charge is 9.375 times 10 to the 4th newtons over coulombs. And the convention for direction is that negatives have all of theirs headed straight towards them. So that field is to the left from over here. So 9.375 times 10 to the 4th newtons per coulomb to the left. So since those are pointing in opposite directions, we're going to subtract. We're going to have the 2.344 to the right. I'm going to say right is positive, left is negative. 2.344 times 10 to the 4th minus 9.375 times 10 to the 4th is negative 7.03 times 10 to the 4th. And since that's negative, that means it's to the left. And field is still newtons divided by coulombs. It can get a little bit more dicey than that, though, when you've got a distribution in 2 dimensions. So I'm not going to actually complete this whole example problem. I'm just going to kind of walk you through how it should be done, and you can figure out the details on your own. That's mostly because it's late, and I'm tired, and I'm not even sure people watch these. So if you watch this and you really wanted me to work out this entire example problem, please email me, and I'll re-video this one problem. Okay, so we're going to determine the magnitude and direction of the electric field at point A, where we've got some unknown test charge that we're going to assume to be positive. Cool. Anyway, so we're going to start with, let's say, this charge right here, the 10 nanocoulomb charge. So we know the electric field due to a point charge equals K times the charge, 10 times 10 to the negative 9th coulombs. Pretend you can read that. Divided by the radius squared. The radius squared is 2 centimeters squared, which in meters is 0.02 meters squared. Put that in your calculator and you'll get a handy dandy 2.25 times 10 to the 5th newtons divided by coulombs. And that one is going to be in the direction away from the positive, because positive points out, which is to the right. So 2.25 times 10 to the 5th newtons per coulomb to the right. Now you do the same thing for the other 2 charges. You calculate out that magnitude using electric field of a point charge equals K times Q over R squared. So you calculate that for each of these 2 things. The positive is going to be pointing away, so you're going to have a vector down here, vector to the right here, but the negative is going to be attracting it or pulling it towards it. And besides, that's not even the point. The convention is that negative things have electric field headed towards them. Okay, their electric field points towards them. So you're going to take this magnitude and this magnitude. They're already in X component, Y component. This one only has X. This one only has Y. But this one right here, when you find it, you're going to break it down into its components. To do that, you use this lovely right triangle. You can use trig, which is the long way. You could find this angle and then use that to find each of the sides, or you can just use similar triangles and proportions, whatever. You add up all of the x's. So you just take this x component here and the x component of this field, and that'll be your x component. Same thing with the y components. And after that, you can determine the magnitude using Pythagorean theorem and the direction using tangent of the two components, the ratio of the two components. So if none of that made sense, if it was too fast for your taste, email me. I'll help you out. Moving on. Our next topic is capacitors. So really only going to deal with parallel plate capacitors. A parallel plate capacitor is two pieces of metal that are approximately, or pretty much definitely, of equal area and of equal but opposite charge. And they're going to be separated by some distance d. Okay. Right now, we don't care about that distance because it's not going to be a big deal here while we're working in electric fields. So what happens in a parallel plate capacitor is that you've got a bunch of charges evenly distributed, because metal is a conductor, and they're evenly distributed on the surface. So we don't really care about the thickness of the metal. We just care about the surface area of the metal. So what happens with the electric field here is that all of the horizontal components end up canceling out due to a charge's neighbors, which is a really weird phenomenon to just kind of think about. But if you do it mathematically, if you want to figure it out mathematically, it is something that is not too difficult to prove. But if you don't want to deal with that, you can just take my word for it. All of the horizontal components cancel, and the electric field only points from the positive side towards the negative side. This results in what we call a uniform electric field. So that means the field is pointed in the same direction everywhere, as you can see. And this is not a very obvious result, but everywhere in there has the same magnitude of electric field. So inside the capacitor, there's a very specific equation that I will not derive for you for the electric field inside the capacitor. And it's written right here. Electric field of the capacitor equals Q, which is the charge of one side, divided by epsilon naught, which is the permittivity of free space, and it's found on your formula chart, times the area, which is the area of the plate. And it's the area of one plate of one side. So you use charge of one side and area of one plate. You don't add the two together or anything like that. So that's how you would find the field inside a capacitor. Why do you need to find the field inside a capacitor? Well, because it's a common physics scenario that pops up a lot. It's used in circuits, but mostly because it was next in the book and because AP said so. Last thing to note about this is that anytime you find the electric field inside a capacitor, the direction of the field is from the positively charged side to the negatively charged side. So if these are the two plates of our capacitor, field lines go from, pretend those are all negatives, go from positive to negative, and they're all the same magnitude. I feel like that is a fairly easy equation. There's not any vector addition involved, so I'm not going to work an example. Again, if you have a question, let me know. That's it for this video. You do have a homework that is posted that will be due tomorrow. Get cracking on it, and let me know if you need help.